In earlier lecture, we have discussed the linear operators, bounded linear operators and also some unbounded linear, non-linear operators also. Now, most of the linear operators, when they are defined over certain, then boundedness will imply the continuity and so on. So, it is a very smooth way dealing with the linear operators, but all the linear operators need not be bounded. So, all linear operators need not be bounded operator. For example, if we look the operator say differential operator, which is a unbounded operator. Why? Because let us suppose let x be the norm space of all polynomials on J close interval 0 and 1 with norm given by norm of x as the maximum of mod x t, where t ranges from 0 to 1 over J, and a operator, a differential operator T is defined on x y t x t equal to x prime t. Okay. Now, if we define the operator T in such a way, then we see that this operator clearly is a linear operator, because you replace x by alpha x plus beta y, accordingly the derivative will come here and we get the linear. But T is not bounded. Why? Because if we look the say operator particular elements say in J like x and t is suppose t to the power n. This is an elements belonging to 0 1 j 0 1, is it not a set of all polynomials belonging to x. This belongs to x basically, where belongs to x, set of all polynomials, because it is a polynomial, and t lying between 0 and 1. Okay. Now, what is the norm of x n? Maximum of this is 1, but t of x n t is equal to n t n minus 1, and norm of t of x n is nothing but n, because the norm of t to the power n will be 1. Therefore, norm of t which is norm of t x n over norm of x n, supremo is taken all x such that norm of x n is 1, that will be equal to n. Okay, but n is arbitrary, so but n is arbitrarily large, one can take. So, we cannot get a constant c such that modulus norm of t n x is less than or equal to c times norm of x. We cannot get a constant c which satisfy this condition, Therefore, T is unbounded. So, here we have seen one example which is a linear operator, what is an unbounded operator. And you know the differential operator plays a vital role in developing the calculus or the theory of the calculus, quantum mechanics theory. They use very widely this differential operator and many other branches where you require the differential operator. So, most of this application part requires the unbounded linear operators, clear. But it so happens that these all linear operator or unbounded these type linear operator, these linear operators so far we have discussed, though they are unbounded, but they are closed. Okay. So, we can say that instead of choosing the linear operator, if we start with the theory of a closed linear operator, if we start with the closed linear operator, then one can get more and more results in comparative to only the linear operator. Okay. So, here we will discuss today the concept of the what is the closed linear operator, and then under what condition this closed linear operator becomes bounded. Okay. So, that we will discuss. That will leads to the important theorem which is known as the closed graph theorem. In fact, this is gives you a sufficient condition on a closed linear on a linear operator, okay, closed linear operator to be bounded. So, let us see first what is how to define the closed linear operator. Clear? Now, when we go for this definition, let us see closed linear operator. Let x and y be norm spaces, V norm spaces, and T are mapping from the domain dt to y a linear operator with domain dt contained in x or subset of x. Then T is called closed linear operator if its graph this we will denote by GT, which is the set of all ordered pair x y such that x belongs to the domain of T and y is the image of x under T, is closed in the norm space x cross y, where the operation on x cross y is defined as well where the addition and scalar multiplication on x cross y is defined as x 1 y 1 is one element, x 2 y 2 another element. The addition is defined as x 1 plus x 2 y 1 plus y 2, and alpha times of x comma y is defined as alpha x alpha y, and the norm on this x ordered pair x t is defined as norm of x plus norm of y, where the x belongs to capital X and y belongs to capital Y. Okay. So, if we use these operations, then x cross y becomes a vector space, okay, and under this thing it becomes a norm space. Now, this is not only the norm, we can also define the norms in some other way, like the maximum of norm x and norm y. This is another way, or maybe we can define under root this square plus this square under root of this, that is also a norm. So, there are many ways of defining the norm, but we are choosing the norm in this way. Okay. So, what is that closed linear operator is basically, and linear operator is said to be closed when its graph is closed. What do you mean by the graph is closed? This graph is closed means that, so let us discuss this. Okay. So, we say a linear operator T is closed if and only if its graph is closed, is it not? T is closed means if and only if its graph, sorry, if its graph zeta t is closed. Okay. What do you mean by this zeta t is closed? Zeta t is closed means it contains all of its limit points. So, zeta t is closed if and only if all of its limit point belongs to it, if and only if, that is, if I take a point z in the closure of this set, okay, then it implies z belongs to this, implies that z belongs to zeta t, is it not? Z belongs to zeta t, that is what meaning. Now, what is the meaning of this? Z x by belongs to zeta bar means that there will be a sequence x n z n in zeta which converges to z under the topology, under that norm. So, this means as that if and only if there are sequences z n, x n by n in zeta t belongs to zeta t, okay, belongs to zeta t, belongs to zeta t, such that zeta n, this z n will go to, is it not, z n will go to z which is x y, is it not? It means the coordinate wise convergence is there, hence x n will go to x and t of x n will go to y, okay, and this z which is x y must be a point in zeta t. Okay. It means, this means, so z which is x y belongs to zeta t if and only if, when it belongs to the zeta t, when a point belongs to the graph of t, when x is lying in the domain of t and y must be the image of that. So, if and only if x belongs to the domain of t and image y is the image of x under t. Okay. So, that is the meaning when we say a operator is closed if its graph is closed and when graph is closed means basically we are having this thing. So, what is the meaning of graph is closed means that there must be a sequence, or if we take any point in the closure of this, that point must be the point of the zeta t. It means the x coordinate must be the point of dt and y coordinate should be the image of dt. Now, this whole discussion leads a very important result which will be used frequently and also as a definition of the closed linear operator. So, we say this leads the following theorem, and it can be taken as a definition of closeness of a linear operator. Okay. Now, what is this theorem? The theorem is let us see here itself we can start theorem, which we call it as a closed linear operator. That is also a definition one can use. So, let x and let t is a mapping from domain dt to y be a, where dt is a subset of x, okay, be a linear operator where dt is a subset of x. X and y are norm spaces. Norm spaces, okay, are norm spaces. Okay, that's let t be a linear operator, dt in the spaces. Then T is closed if and only if it has the following property. Following property, the property is if x n converges to x, where x n is a sequence in dt and image of x n under t goes to y, then x must be in the domain dt, x will be in domain dt and image of x under t must be y. Now, this definition is a if and only part. Earlier we have started the definition of the closed linear operator in terms of the graph. What we told, a linear operator will be a closed or linear operator if the graph is closed, but graph is closed leads to this definition which is if and only part. So, finally, we can say T is closed if we have, and this is very easy to apply. In order to prove or to just verify whether the operator is a closed linear operator or not, what we do is we simply pick up a sequence x n in the domain dt whose limit point is x, okay, then find out the images. If that image also converges to y, then we find the relation between y and t. If y comes out to be t x and limit point x is in t dt, then only we say it is a closed linear operator. Now, this concept is entirely different from the concept of the continuity. What we say is the continuity, if an operator is a continuous operator, then what we say a sequence x n converges to x will automatically implies the t x n will go to t x. Okay. There is not required at all the convergence of t x n to point y and y is t x, because automatically the continuity will implies when it will transfer the convergence sequence to the convergence sequence. But in case of the closed linear operator, it is not so. What we are doing, we are taking a convergence sequence. This is a convergence sequence, but there is no guarantee that T x n will go to y converge. There is no guarantee. If at all it converges, this is necessary that we have to take the condition that this sequence converges, then only we can relate the image point with this x. And the relation is that y must be T x and x should be the point in domain D t. Okay? Now, domain D t need not be a closed set, because if it is closed, then only all the limits points belongs to it. Okay. So, that also we will see that if it becomes closed, then the closed linear operator becomes bounded. That is what the closed graph theorem says. Okay. So, these two are entirely different concepts. However, there is a similarity, slight similarity is, what is the similarity is, suppose x n and y n are the two sequences converges to a same limit point. The images T x n and T y n will also lead to the same image point, even if the T is a closed linear operator. That is the similar. Okay. So, that problem we can discuss. Okay. So, we are just defining this and get. Now, let us come back to our closed graph theorem. Okay. Under what condition this closed linear operator is bounded? So, theorem which is closed graph theorem. Okay. Now, what is this theorem says? Let x and y be Banach spaces and T is a mapping from the domain D t to y, a closed linear operator, where D t is contained in X, and domain is a subset of X, subspace of course. Then if domain D t is closed in X, then the operator T is bounded. Okay. Clear? So, what is the closed graph theorem says that if T is a closed linear operator from one norm space to one Banach space to another Banach space. Remember, the closed graph theorem, open mapping theorem, these requires the Banach space to Banach. Uniform boundedness theorem requires the Banach to norm, but Hahn-Banach theorem does not require anything. It simply says an functional an operator from one vector space to another vector space. Closeness is not required, but here the closeness is both the x and y is must. Similarly, in case of the open mapping theorem also. Okay. So, x the operator T is bound. So, what it says is this closed linear operator will be bounded when the domain is closed. So, this is the sufficient condition for a closed linear operator to be a bounded operator. And as soon as this is bounded, because it is also linear. So, every linear operator bounded and continuities are the same. So, basically it becomes the continuous operator. Okay. So, that is what. Let us see the proof of it. So, first we will show that our space which is x cross y, because the T is given to be a closed linear operator, it means the graph of T is closed. So, first let us see the graph of T, which is a subspace of x cross y, is a subset of x cross y. It is a complete space, complete norm space. We wanted to show first. Okay. Once it is complete norm space, then because x dt is closed, graph is closed. So, they will become a complete metric space, complete norm space, Banach space, because every closed subspace of a complete space is a complete. So, once they are complete, limiting point has to be in that. So, that is the idea of the proof, okay, behind it. Okay. So, let us we first show that x cross by with norm defined by norm of x comma y is the norm of x plus norm of y. Okay. With this norm is complete. This we wanted to show first. So, how to prove this is complete? Let us take a sequence arbitrary Cauchy sequence Z n in x cross y, and that sequence if converges, the limit point belongs to x cross y, then our space will be a complete norm space. So, let us pick up this sequence, let Z n, which is of the form say x n y n, x n belongs to capital X, y n belongs to capital Y, be a Cauchy sequence, be a Cauchy sequence in x cross y, arbitrary Cauchy sequence in x cross y. Okay. So, by definition of the Cauchyness, for any epsilon greater than 0, there will exist a n such that the difference between norm s z n minus z n will go less than epsilon when n m sufficiently large. So, for the given epsilon greater than 0, so for given epsilon greater than 0, there is an n integer n such that the norm of z n minus z m, this will remain less than epsilon, which is the same as norm of x n minus x m plus norm of y n minus y m is less than epsilon when for all m n greater than capital N. Is it not? Now, once this is less than epsilon, because these are two non-negative terms, is it not? These are two non-negative terms, the total sum is less than epsilon. So, individually each term must be less than epsilon. So, this shows norm of x n minus x m is less than epsilon, as well as norm of y n minus y m is less than epsilon for all m n greater than n. Now, this implies the sequence x n is a Cauchy sequence, sorry, maybe epsilon it hardly matters. I am taking the upper one, epsilon is very small quantity, but we cannot say this is epsilon by 2, this is epsilon by 2, no. It may be possible this is less than epsilon by 4 and this may be less than 3 epsilon by 4. By this total sum has to be less than epsilon, that is all. Whether they may be less than epsilon by 2 each also, or maybe some is less than epsilon by 4, other will be less than 3 by epsilon by 4. So, that is why I did not write epsilon and only this is the upper bound for this. So, this sequence x n and y n are Cauchy sequences in the norm space x and y respectively, is it not? But x and y are complete, are Banach space, this is given. So, it must converge. So, these sequences will converge, x n and y n will converge to x and y respectively, where x belongs to capital X and y belongs to capital Y. Clear? Once we get this, implies that it means this sequence will converge to x and this converges to y. So, our sequence Z n, this sequence Z n will converge to Z which is x y. Is it okay or not? Why? Because in this case, in the, say A star, because in A let m tends to infinity first, keep n is constant. So, what we get, norm of Z n minus Z is less than epsilon. Is it not? Clear? That so, we get this thing is less than epsilon. Clear? So, we get from here is this is less than for n greater than capital N. But Z n is a Cauchy sequence and which converges to a point Z belonging to x cross y, because x. So, Cauchy sequence Z n converges to Z in x cross y. Therefore, x cross y, and it is arbitrary Cauchy sequence, is it not? Any sequence, any Cauchy sequence Z n. Clear? So, x cross y is complete. Norm space means it is a Banach space. Clear? Now, we will show our thing, that is we wanted the operator T to be bounded. So, what we will do is we will first prove the define an operator P from let us say graph of T to dt, which is a bounded linear operator. Then we will apply the open mapping bounded inverse theorem, and bounded inverse theorem will say the inverse operator is bounded, and as a consequence we can say T is a bounded. So, that is again. So, let us assume okay. Now, since the graph of T is closed, this is given by assumption, this is closed in x cross y, okay, and domain of dt. Why it is closed? Because T is given to be a closed linear operator, because this was our theorem, T is a closed linear operator. So, given because T is closed linear operator, that is why, and domain of dt is closed in x. This is also our assumption, this is our assumption given if T is closed. So, graph of T is closed, domain of T is closed in this, therefore, graph of closed that is yeah. So, and consider, so the both are closed, consider, so these are complete norm spaces. Why? Because these are the closed subspace of a complete space, this is also closed subspace of a complete norm space. Therefore, zeta t and delta t both are dt both are a complete norm spaces, subspaces you can say, is it not? Subspaces. Clear? Now, let us define a mapping T P from the graph of zeta t to domain of T, which carries the point x t x to x. Okay. Pick up the point in graph of T and then image this. Now, clearly P is linear and 1 1. Why? Why it is linear? Let us take because domain and graph, the points is graph is a ordered pair x comma by y is equal to T x. So, x comma T x is a point, and what image of this is coming to be a point in dt. So, x. Okay. Now, this is linear. Why it is linear? Because if we take the point say x 1 comma T x 1, okay, and then plus x 2 comma T x 2, and under this the image P. So, what you get is this will be added. So, basically you are getting x 1 plus x 2, that is all, and this is the same as the sum of these two, is it not? Is it clear or not? T is already giving to be a linear. T is already giving to be linear. Is it okay or not? Then alpha of this x T x. So, by definition this will be equal to P of alpha x alpha T x, and this will be equal to alpha x. So, it becomes alpha of P x comma T x. So, it is linear. Is it okay? And why it is 1 1? T is 1 1. It follows very easily. P is 1 1, sorry. So, let us take P x 1 T x 1 is the same as P x 2 T x 2, where x 1 is different from x 2. So, this will give P x 1 means x 1 is equal to x 2. It means, if I take the two images identical, this is only possible when x 1 is equal to x 2. So, this implies P is 1 1. Okay. Then further we claim that P is bounded. P is bounded. Bounded means norm of this image is less than or equal to constant times the norm of A. So, consider norm of image of this. Okay. But what is the P of this? This will give norm x. Now, this is less than or equal to norm x plus norm T x. You are adding one more point real number here, is it not? So, there is the, but this is equal to, is it not a norm of x comma T x by definition? Okay. So, this is norm of A. So, norm of P x is equal to norm of A. It means, the divide by this, norm P becomes 1. So, P is bounded. Okay. There is a C is 1 and then P is bounded. Then further inverse mapping. So, P is 1 1 linear. Okay. It is a linear 1 1. So, inverse exists, okay, and bounded, that also. So, basically the P inverse will exist. So, P inverse. So, the inverse mapping P inverse will be a mapping from domain dt to G, because it is 1 1 on 2 and this inverse exists, and what is this? X will carry to x T x, is it not? That one. Okay. Now, let us come to the bounded inverse theorem. What is the bounded inverse theorem? Yesterday we have discussed it. This theorem says the operator, if a bounded linear operator T from one Banach space to another Banach space is an open mapping, and if T inverse exists, T is bijective inverse, T is bijective, then T inverse is continuous and bounded. So, what is given is that operator P from Banach space to Banach space, this must be an open mapping. Okay. Open mapping means send the open set to open set, and then if T is bijective, okay, then inverse is continuous and thus bounded. So, here everything is because these are all Banach spaces. Okay. So, we can apply the closed linear theorem. So, by say bounded inverse theorem, okay, we say this is inverse operator P inverse is bounded. is it not? P inverse is bounded. Bounded means P inverse means bounded means this is the norm of this. So, x T x norm of this is less than equal to some constant b times norm of x. So, there exists a b such that this is norm of this. Okay. But what is here is let it be b. Okay. But norm of T x, this can be written as less than equal to norm of T x plus norm of x, which is the same as norm of x comma T x by definition. X comma T x is less than equal to b times norm x. So, this will be this implies norm of T x is less than equal to b times norm x. Therefore, T is bounded. Is it okay or not? For all x this is true for all x belongs to the domain T T. So, this implies T is bounded. Clear? Is it okay or not? And that is what we wanted to prove, the operator T. So, this proves the closed graph theorem. Is it clear? Now, so we have discussed these closed linear operators and closed graph theorems and this. Now, what is the relation now? Can you say if the operator is closed, then it will be bounded, or if a operator is bounded, can you say it is closed, or none of the statement holds in general? Is it not? Just like continuity and boundedness we have, if the operator is linear operator, then continuity and boundedness are the same thing. Okay. But here the closeness and boundedness, whether they can also be related, or if not, then we should have certain examples where it violates. So, basically here we say none of these statement is true, means a closed operator need not be bounded always. Similarly, a bounded operator need not be closed also. Okay. So, this is the result which we wanted to discuss. Closeness does not imply boundedness, of a linear operator. Conversely, boundedness does not imply closeness. Okay. Let us see this result. So, for example, is first we will show that the operator is closed but not bounded. Every closed operator need not be bounded. Every closed linear operator need not be bounded. Okay. This we have seen already. For example, a differential operator discussed earlier. Is it not? If we define the mapping T from the set of all polynomial over the interval 0 1 and define the T x equal to x prime t, we say that operator is not bounded operator, is not bounded. For example, closeness. That is why. So, let us take the operator differential operator T is not bounded operator, but linear, is it not? Linear bounded. Now, let us see that whatever the differential operator, that is an operator T from C 0 1, is it not, to C 0 1, such that the image of this goes to x prime derivative and like this. Okay. So, this operator was not linear, was linear, but not bounded. Okay. Now, let us see, we claim that this operator T, that this T is closed. Okay. So, how to prove this closeness is, okay, let us take closed means graph T must be closed, or if we prove that domain of dt is closed, is it not, x n x belongs to dt and t x belongs is by, then it is also closed by, because that result operator T is closed when x n converges to x and the T of x n goes T x n converges to y, x belongs to dt and y is equal to T x, then it is closed. So, we will use this control. Okay. So, let us take, let x n in domain dt be such that both a sequence x n and the image T x n converges, because for the closeness this condition is required, is it not? T x n must converge, then only the y and x can be related to T x. Okay. Converges. Say x n converges to x and T x n, which is the derivative of x n, converges to y. Okay. Clear? Now, this convergence is in the, in which, in C 0 1, is it not? C 0 1 the convergence is uniform, because it is the maximum of mod x n minus by t is linear or integral part. Okay. So, since the convergence in the norm of C 0 1 is uniform, is uniform convergence, is it okay or not? Convergence on the interval 0 1. So, from this, from x n dash converges to x dash, from derivative x n dash converges to y, we have this integral 0 to 1 by tau d tau is the integral 0 to t, sorry 0 to t, 0 to t, integral 0 to t, by t is the limit of, by tau is the limit of x n prime tau when n tends to infinity, d tau, this is just by def. Okay. Because C 0 1 the integral, the makes norm can also be defined in terms of the integral. So, this is okay, and this is nothing but what, because the derivative exists. So, we can take the, and limit is a continuous function. So, we can take the limit outside, we can say limit n tends to infinity and then integral 0 to t x n prime tau d tau, okay, d tau, and then this will give you differentiate, integrate it. So, x n tau, so the value will come to x n t minus x 0, minus x n 0, sorry, this limit is what, limit is x t, I am sorry, this limit, okay, and then limit of n, this will give x t minus x 0, is it okay or not? clear, x t minus. So, this implies that x t is nothing but x 0 plus integral 0 to t by tau d tau.
Sir, limit n tends to infinity. So when n tends to infinity, so x and t converges to xt.
Huh. By this, why I have taken limit? Because the integration been required. Okay, that is all. So, this shows that x belongs to dt. Y and x prime is y. Why x belongs to dt? Because what is the dt? dt is because dt is a subset of C 0 1, set of all functions. This C 0 1 have a continuous derivative. Okay. dt is the dt x well dt is the set of all functions x which have continuous derivatives. Okay. So, that is why this is a x limit point belongs to dt, because it is a continuous now, because this is continuous, integral part is continuous. Okay. So, x t will be a continuous function of t. This is, in fact, it is differentiable and derivative will come out to be by the first principle of differential calculus. Okay. First principle. So, we get from here this, hence this implies t is closed, because y is equal to t x. So, this t is closed. Okay. So, it is a
And sir, x0 will not.
x 0 is constant.
How is a constant?
So, it will not defect. So, it is okay. So, it is a bounded linear operator, is it not? This operator is a unbounded linear operator, but it is closed. Okay. Now, the second part we will discuss next time tomorrow. Okay. Thank you, because it requires certain. Okay. Nice.